a deep dive into vector databases and retrieval augmented generation for the technical interview. Part 1. The Foundation, Vector Databases and Embeddings. A new paradigm for data, the rise of the vector database. The modern data landscape is undergoing a profound transformation. Historically, databases were designed to manage structured information, data that fits neatly into the rows and columns of a table. However, the exponential growth of unstructured data, such as social media posts, images, videos, and audio clips, has exposed the limitations of these traditional systems. This surge in complex, unstructured information has catalyzed the development of a new database paradigm, the vector database. At its core, a vector database is a specialized system designed to store, manage, and search high-dimensional vector embeddings. Unlike a traditional database that retrieves data based on exact matches to keywords or values, a vector database operates on the principle of conceptual or semantic similarity. It stores data not as discrete values, but as mathematical representations in a multidimensional space, where the geometric distance between two vectors indicates their semantic similarity. This allows for powerful new forms of querying. For example, a search for smartphone might return results for cell phone and mobile devices, concepts that are semantically related but textually distinct. This approach stands in stark contrast to legacy database architectures, relational databases, SQL. These systems excel at managing structured data with rigid schemas, enforcing transactional integrity through ACID compliance. They use structured query language for complex queries involving joins across multiple tables. However, their indexing and query mechanisms are built for exact match lookups and are fundamentally unsuited for the geometric calculations required for similarity search on unstructured data. NoSQL databases, emerging to handle the volume and variety of web-scale data, NoSQL databases offer flexibility with dynamic schemas and horizontal scalability. They manage semi-structured data like JSON documents or key-value pairs effectively, but like their relational counterparts, are not purpose-built for the unique challenges of indexing and querying high-dimensional vectors. The very existence of vector databases is a response to a fundamental mismatch. Traditional databases are indexed on discrete values, making queries like where name equals John highly efficient. Unstructured data, however, lacks such discrete, indexable features. Its value lies in its meaning. Machine learning models can translate this meaning into a numerical vector, but a traditional database cannot efficiently answer a query like where vector is conceptually similar to another vector. This is a geometric proximity problem, not a simple filtering task, and it requires a new architecture whose core operations are built around calculating distances in a high-dimensional space. Consequently, vector databases have become the foundational infrastructure for a wide range of modern AI applications, including recommendation engines, anomaly detection, image and video retrieval, and, most critically, as the external knowledge base for large language models, LLMs, in retrieval augmented generation, RAG systems. The art of vectorization, translating reality into numbers. The process of converting unstructured data into the numerical format that vector databases can manage is called vectorization, and the resulting numerical arrays are known as vector embeddings. An embedding is a compact numerical representation of a data point, be it a word, a sentence, or an image, within a continuous multidimensional space. The defining characteristic of this process is that semantically similar items are mapped to points that are geometrically close to one another in this vector space. This translation from abstract concept to numerical vector is achieved through a process called representation learning, which is typically performed by deep neural networks. A model is trained on a massive data set to perform a specific task, such as predicting the next word in a sentence. In learning to perform this task, the model's internal layers inherently learn to create dense, meaningful numerical representations of the input data. These embeddings are a form of lossy compression, where the most crucial semantic relationships and features of the original data are preserved while irrelevant information is discarded. The techniques for creating text embeddings have evolved significantly, a progression that is critical to the success of modern RAG systems. Early models, word-to-vec glove. These pioneering models generated a single static vector for each word in a vocabulary. While they successfully captured semantic analogies, such as the famous king-man plus woman approximately equals queen relationship, they were context agnostic. This meant they could not differentiate between the multiple meanings of a polysemantic word like bank, a financial institution versus a river's edge, assigning it the same vector in all contexts. Transformer models, BERT. The development of the transformer architecture with its core attention mechanism was a major breakthrough. Models like BERT, bidirectional encoder representations from transformers, can consider the entire context of a sentence when generating an embedding for a word. This allows them to produce different vectors for the word bank, depending on its surrounding text, thus capturing its intended meaning with much higher fidelity. Sentence BERT, SBERT. While BERT is powerful, its native outputs are not optimally structured for semantic similarity search. Using the embedding of its special token, for instance, often yields poor performance in sentence-level comparison tasks. Sentence BERT is a modification of the BERT architecture that uses a Siamese network structure to fine-tune the model specifically for the task of producing semantically meaningful sentence embeddings. It is trained to ensure that similar sentences are mapped to nearby points in the vector space, making it exceptionally effective for the kind of retrieval tasks required by RAG systems. Models like all mini ML6v2, which maps sentences to a 384-dimensional vector, are widely used for this purpose. The quality of a RAG system is inextricably linked to the quality of its embedding model. The transition from context-agnostic to context-aware embeddings was the pivotal innovation that enabled the high-performance semantic search necessary for modern RAG. A RAG system's ability to retrieve relevant documents hinges on the precision of its embeddings. If an embedding model cannot capture the specific nuance of a user's query, it will generate a generic vector, leading to the retrieval of superficially related but ultimately irrelevant documents. This provides poor context to the LLM and results in a low-quality answer. Therefore, the capacity of models like SBERT to generate highly specific, context-aware sentence embeddings is the technological bedrock upon which effective RAG is built. Measuring meaning. Similarity metrics. Once data is represented in a vector space, a vector database needs a method to quantify the closeness between vectors. This is accomplished using similarity metrics, which calculate a score based on the geometric relationship between two vectors. The two most prevalent metrics are Euclidean distance and cosine similarity. Euclidean distance, L2 norm. This metric represents the straight line or ruler distance between two vector endpoints in the multidimensional space. It is calculated as the square root of the sum of the squared differences between corresponding vector components. Euclidean distance is sensitive to both the magnitude or length and the direction of the vectors. It is most appropriate when the magnitude of the vector carries meaningful information. For instance, in a recommendation system where vector magnitudes might correlate with user engagement levels. A larger Euclidean distance could signify a meaningful difference in user behavior. Cosine similarity. In contrast, cosine similarity disregards magnitude and measures only the angle between two vectors. Its value ranges from -1, vectors pointing in opposite directions, to 1, vectors pointing in the same direction, with 0 indicating they are orthogonal. This metric is ideal for semantic text search, where the direction of a vector represents its meaning and its magnitude, often influenced by factors like document length, is something to be ignored. Two documents discussing the same topic should have vectors pointing in a similar direction, even if one is significantly longer than the other. While both metrics are useful, the cardinal rule for selection is to use the same similarity metric that was used to train the embedding model. An embedding model learns to structure the vector space according to a specific geometric objective. If a model was trained to group similar documents by minimizing the angle between their vectors, optimizing for cosine similarity, then the magnitude of those vectors is effectively noise. Using Euclidean distance in this scenario would incorrectly penalize vectors for having different magnitudes even if they are semantically identical, thereby corrupting the semantic structure the model learned to create and leading to poor search results. Part 2, the engine room, vector search and indexing, the challenge of scale, from exact to approximate search. The most direct method for finding the most similar vectors to a given query is to perform an exhaustive, brute force comparison. This approach, known as an exact k-nearest neighbor, KNN search, or a flat search, involves calculating the distance between the query vector and every other vector in the database. While this guarantees finding the absolute closest neighbors, its computational complexity is linear, denoted as big O of n, where n is the total number of vectors. For datasets containing millions or billions of vectors, this linear scan becomes computationally prohibitive, rendering real-time applications impossible. To overcome this computational barrier, vector databases employ approximate nearest neighbor ANN search algorithms. ANN techniques fundamentally alter the problem by trading a small, often imperceptible, amount of accuracy for monumental gains in search speed and efficiency. Instead of guaranteeing the discovery of the absolute nearest neighbors, ANN algorithms aim to find vectors that are close enough with a very high probability, typically achieving logarithmic time complexity, or big O of log n. This trade-off is not merely acceptable, but highly desirable for semantic applications. The nature of high-quality embeddings is such that semantically similar items are clustered closely together in the vector space. Therefore, the difference in relevance between the absolute top result and the second or third closest result is often negligible from a user's perspective. For a query like, "What are the benefits of RAG?" an ANN search might return the second best matching document chunk instead of the absolute best. However, that second best chunk is still extremely likely to contain a highly relevant and correct answer. The orders of magnitude improvement in speed and reduction in computational costs far outweigh the marginal loss in perfect recall, making the overall user experience faster and more practical at scale. Navigating the graph, the HNSW algorithm. Among the various ANN algorithms, one of the most popular and effective is the hierarchical navigable small world HNSW algorithm. HNSW is a graph-based approach that organizes data points as nodes, vertices, within a multi-layered graph, where connections, edges, link similar vectors. The design is inspired by the concept of a skip list, a data structure that uses multiple layers of linked lists to speed up search. The structure can be visualized as a multi-layered transportation network. Layer 0, the bottom layer. This is the densest layer, containing every single vector in the dataset. It functions like a map of local streets, where each house, vector, is connected to its immediate neighbors. This layer allows for highly precise, fine-grained navigation, but is slow for traversing long distances. Higher layers. These layers are progressively sparser subsets of the layer below. They act as highways and expressways, creating long edges that connect distant points in the vector space. These long-range links enable rapid traversal from one region of the graph to another. The search process leverages this hierarchy for a coarse-to-fine navigation strategy. A search begins at an entry point on the topmost, sparsest layer. The algorithm greedily follows the expressway links to quickly navigate to the general vicinity of the query vector. It then descends to the next layer down, the highways, to perform a more refined search within that neighborhood. This process is repeated, moving from broader to more granular layers until the search reaches the dense bottom layer of local streets, where it identifies the final set of nearest neighbors. The brilliance of HNSW lies in its hierarchical structure, which effectively solves the local minima problem that can trap simpler graph search algorithms. A basic single-layer graph search might start in a dense cluster of vectors that is far from the true best match. It would find the best match within that cluster and incorrectly conclude its search, never discovering the better results in a different region of the graph. HNSW's upper layers, with their long-range connections, act as bridges between these disparate clusters. By starting the search at the highest level, the algorithm gains a global perspective, ensuring it identifies the most promising global region before committing to a local search in the denser, lower layers. The performance of an HNS-W index can be tuned via several key parameters, such as M, which defines the maximum number of connections per node, and F construction and F search, which control the depth of the search during index building and querying respectively. These parameters allow for a fine-tuned trade-off between index quality, build time, search speed, and accuracy. Compressing reality, quantization techniques. A significant practical challenge for vector databases is the immense memory footprint required to store billions of high-precision vectors. Since high-performance indexes like HNS-W must be loaded into system RAM, the cost and scalability of a vector search system are often constrained by memory limitations. Vector quantization addresses this problem by using lossy compression techniques to reduce the memory required to store each vector. It is important to distinguish this from dimensionality reduction. Quantization reduces the scope or precision of the values within a vector, not the number of dimensions. Scalar quantization, SQ. This is the most straightforward method. It compresses vectors by mapping each high-precision floating point value, e.g., a 32-bit float, to a lower precision integer value, e.g., an 8-bit integer. This can achieve a compression ratio of up to 4 times with a manageable loss of precision. Product quantization, PQ. This is a more sophisticated and powerful technique that enables much higher compression ratios. PQ employs a divide-and-conquer strategy. Splitting. A high-dimensional vector is first divided into several smaller, equal-sized subvectors. For example, a 1024-dimension vector could be split into 8 subvectors of 128 dimensions each. Subquantization. A separate clustering algorithm, typically k-means, is run independently on the collection of subvectors within each of the 8 segments. This process generates a small, distinct codebook of representative centroids for each subspace. In coding, the original vector is then compressed into a short code composed of the IDs of the nearest centroids from each respective codebook. If each of the 8 subspaces has 256 centroids, each 128-dimension subvector can be represented by a single 8-bit integer, its centroid ID. The entire 1024-dimension vector is thus replaced by a tiny 8-byte code, achieving a dramatic 512 times compression in this example. Product quantization's effectiveness comes from its clever circumvention of the curse of dimensionality in clustering. Attempting to run a single KO means clustering algorithm to find a sufficient number of centroids in a 1024-dimensional space would be computationally intractable. By decomposing this into 8 independent clustering problems in a much lower 128-dimensional space, PQ makes the problem tractable. This method achieves an exponential increase in representational power. The effective number of virtual centroids is the product of the centroids in each subspace, e.g. 256. 8. For only a linear increase in storage cost, the sum of the codebooks, making it a highly efficient compression strategy for large-scale vector search. Part 3. The application, Retrieval Augmented Generation, RAG. Grounding LLMs in reality. RAG is an AI framework that dramatically enhances the capabilities of large language models by connecting them to an external, authoritative knowledge base, typically a vector database. This architecture allows the model to retrieve relevant, factual information in real time and use that information as context to generate its response. A useful analogy is that of an open book exam. A standard LLM operates like a student taking a closed book test, relying solely on information memorized during its training phase. This knowledge is static and can become outdated. In contrast, a RAG-enabled LLM is like a student who can consult a textbook, the vector database, before answering a question, ensuring the answer is based on accurate and current information. The core value of RAG lies in its ability to address several inherent weaknesses of standalone LLMs. Mitigating hallucinations. LLMs are known to hallucinate or invent facts when they do not know the answer to a question. By grounding the generation process in specific, retrieved factual data, RAG significantly reduces the model's tendency to confabulate. Access to current and proprietary data. The knowledge of an LLM is frozen at the time of its training. RAG overcomes this limitation by allowing the model to access up-to-the-minute information from live data sources or to query private, domain-specific knowledge bases, such as a company's internal documentation, without the need for constant retraining. Cost effectiveness. Fine-tuning or fully retraining an LLM to incorporate new knowledge is a computationally intensive and expensive process. RAG offers a far more agile and cost-effective method for injecting new information into the system. Transparency and trust. Because the LLM's response is based on retrieved documents, a RAG system can cite its sources. This allows users to verify the information and understand the basis for the model's answer, which is crucial for building trust and accountability. Fundamentally, RAG redefines the role of the LLM. It decouples the knowledge component of the system from the reasoning and language component. A standalone LLM conflates these two roles, which is inefficient because factual knowledge changes rapidly, requiring expensive updates to the model's parameters. In a RAG architecture, the vector database serves as a dynamic, easily updatable external memory. The LLM is then freed to focus on its core competencies, understanding the user's intent, interpreting the retrieved context, and synthesizing that information into a coherent, well-formulated response. This modular design represents a more robust and scalable architecture for building knowledge-intensive AI applications. The standard RAG workflow. The RAG process can be divided into two main phases: an offline ingestion phase where the knowledge base is prepared, and an online retrieval and generation phase that occurs in real time when a user submits a query. Phase 1. Ingestion offline process. This phase prepares the external knowledge for retrieval. Load documents. Data is ingested from various sources, such as text files, PDFs, or websites. Chunking. The loaded documents are segmented into smaller, manageable pieces or chunks. This step is critical for retrieval quality and is explored further in Part 4. Embedding. Each chunk of text is processed by an embedding model, e.g. SBERT, to convert it into a numerical vector embedding. Indexing. The vector embeddings along with their corresponding text chunks and any relevant metadata, like source document ID or creation date, are loaded into a vector database, which builds an efficient index, e.g. HNSW, for fast searching. Phase 2. Retrieval and generation online process. This phase is triggered by a user query. User query. A user submits a query in natural language. For example, what is our company's policy on parental leave? Query embedding. The user's query is passed through the exact same embedding model that was used during the ingestion phase. This creates a query vector that exists in the same semantic space as the document vectors. Similarity search. The vector database uses the query vector to perform a similarity search, e.g., using an ANN algorithm like HNSW, and retrieves the top K most similar document chunks. These chunks are the most semantically relevant pieces of information from the knowledge base. Prompt augmentation. The retrieved text chunks are combined with the original user query to form an augmented prompt. This prompt is carefully engineered to provide the LLM with both the necessary context and the user's question. For example, context. Question: what is our company's policy on parental leave? Answer: LLM generation. This augmented prompt is sent to the LLM. The model then synthesizes the information from the provided context to generate a final, factually grounded answer in natural language. Part 4. Advanced Retrieval Strategies for Production-Grade RAG. The Art of the Split, Document Chunking Strategies. The process of splitting documents into chunks is one of the most critical factors influencing the performance of a RAG system. It presents a fundamental trade-off. Small, granular chunks tend to produce more precise and semantically focused embeddings, which improves the accuracy of the retrieval step. However, these small chunks may lack the surrounding context necessary for the LLM to generate a comprehensive answer. Conversely, large chunks provide ample context but can dilute the semantic meaning of their embeddings, making it difficult for a specific query to find a strong match. Optimizing this trade-off requires selecting an appropriate chunking strategy for the specific type of data being indexed. Common methods include fixed size chunking, the most straightforward approach, where text is split into chunks of a predetermined character or token count. An overlap between consecutive chunks is often used to mitigate the risk of cutting off a coherent thought mid-sentence. While fast and simple, this method is naive as it ignores the natural semantic and structural boundaries of the text. Recursive chunking, a more sophisticated method that attempts to preserve semantic coherence. It uses a prioritized list of separators, e.g., paragraph breaks, followed by sentence breaks, then spaces, and recursively applies them to split the text until the chunks are of a desired size. This strategy is often a recommended starting point as it respects the document's structure as much as possible. Content-aware chunking. This strategy leverages the inherent structure of the source document. For example, it might split a markdown file based on its headers, a code file by its functions or classes, or a presentation by its individual slides. This is highly effective for structured or semi-structured documents. Semantic chunking, an advanced technique that splits text based on semantic similarity. The algorithm analyzes the embeddings of consecutive sentences and creates a chunk boundary when the semantic meaning between them diverges beyond a defined threshold. This results in chunks that are exceptionally coherent and thematically focused. The choice of chunking strategy is a form of feature engineering for retrieval. It directly defines the searchable units of the knowledge base. A poor strategy that splits a single idea across two chunks may cause the retrieval system to only fetch one part, providing the LLM with incomplete context and leading to a partial answer. An effective strategy creates chunks that are both semantically coherent and contextually self-contained, optimizing the performance of the entire RAG pipeline. The second pass, the role of re-rankers. While vector similarity search is highly effective at retrieving a broad set of potentially relevant documents, it is not perfect. The embedding process compresses complex information into a fixed size vector, which can lead to a loss of nuance. As a result, the initial top K retrieved documents are strong candidates, but their ordering may not be optimal, and some less relevant documents may be included. A re-ranker is a second-stage model that refines this initial set of results. It takes the list of candidate documents from the retriever and reorders them using a more computationally intensive, but more accurate assessment of their relevance to the original query. This two-stage process typically involves two different types of models: retrieval by encoder. The initial fast retrieval is performed by a by-encoder model, like SBERT. It generates embeddings for the query and the documents independently. The comparison is then a very fast calculation, e.g., cosine similarity, because all document embeddings can be pre-computed and indexed. Re-ranking cross-encoder. The re-ranker is usually a cross-encoder model. Instead of processing the query and documents separately, it takes them together as a single input pair. This allows the model to perform a deep, token-by-token analysis of the interaction and relationship between the query and the document, producing a highly accurate relevance score. This process is much slower and cannot be pre-computed, which is why it is only applied to the small subset of documents returned by the initial retriever. This retrieve then re-rank architecture is a classic engineering pattern that creates a performance accuracy cascade. It uses a fast, scalable, but less precise method to drastically narrow the search space from millions of documents down to a few dozen. Then it applies a slow, expensive, but highly precise method to that small, manageable set. This hybrid approach provides the scalability of vector search with a high precision of a cross-encoder, delivering superior results while also reducing the amount of irrelevant noise passed to the LLM, which in turn saves on token costs and improves the quality of the final generated answer. Balancing precision and context, parent document and hierarchical retrievers. Advanced retrieval techniques offer solutions to the chunking dilemma of balancing retrieval precision with generation context. The parent document retriever is a particularly elegant strategy that directly addresses this challenge. The workflow is as follows: ingestion, Documents are split twice. First, they are broken into larger, contextually rich parent chunks. Then each parent chunk is further divided into smaller, semantically focused child chunks. Indexing, critically, vector embeddings are created and indexed only for the small child chunks. The larger parent chunks are stored in a simple key-value document store, linked to their children by an ID retrieval. When a user query is received, the similarity search is performed against the precise embeddings of the child chunks. Once the most relevant child chunks are found, the system uses their metadata to look up and return their corresponding full parent chunks. This method provides the best of both worlds: the highly accurate, targeted retrieval that comes from searching over small, specific chunks, combined with the rich, complete context from the larger parent chunks that the LLM needs to generate a high-quality answer. A related, more general concept is hierarchical retrieval. This involves structuring information in multiple layers and performing a multi-step search. For instance, a system could first perform a search over document summaries to identify a small set of highly relevant documents. In a second step, it would then perform a more granular search only within the full text of those selected documents. This top-down approach efficiently narrows the search space, making it particularly useful for extremely large or complex knowledge bases. These advanced strategies show that production-grade RAG is not just about finding similar vectors. It's about intelligently managing the granularity of information at different stages of the pipeline to optimize for both retrieval accuracy and generation quality. Part 5. The Ecosystem, a comparative overview of leading vector databases. Architectural philosophies. The vector database market includes several prominent players, each with a distinct architectural philosophy that makes it suitable for different use cases and operational models. Pinecone. Pinecone is built on a fully managed, serverless-first philosophy designed to abstract away infrastructure complexity. Its architecture features a separation of the control plane for managing resources and the data plane for handling data operations. Within the data plane, read and write paths are also separated, allowing them to scale independently. A key innovation is its use of immutable files called slabs, stored in distributed object storage, which decouples storage from compute. This enables highly efficient, cost-effective scaling for on-demand and bursty workloads, making it ideal for teams who want to focus on application development rather than database administration. Weaviate. Weaviate is an open-source database with a managed cloud offering built around a philosophy of modularity. It is designed using a clean architecture, which allows various components, such as vectorization models or storage backends, to be plugged in as modules. For its distributed architecture, it employs a leaderless replication design for data to ensure high availability, while using the RAF consensus algorithm for metadata to maintain consistency. Weaviate has a particularly strong focus on enabling flexible hybrid search, combining traditional keyword-based search with semantic vector search. Milvus. Milvus is an open-source project architected for massive industrial-scale deployments. Its cloud-native design is highly disaggregated, featuring 4 distinct layers: access, coordinator, worker, and storage, that can be scaled independently. This deep separation of concerns, querying, data ingestion, and indexing, allows for extremely fine-grained resource allocation and optimization, making it suitable for handling datasets with billions of vectors. It is best suited for large enterprises that have dedicated data engineering and operations teams to manage its complexity. Chroma. Chroma is an open-source, developer-first vector database designed to be lightweight and easy to use. Its primary goal is to simplify the process of building LLM applications. It can run embedded directly within a Python script for rapid prototyping or as a single-node server for small to medium-scale applications. Its architecture is composed of modular components like a gateway, log, and query executor, and it prioritizes a simple API and tight integration with popular machine learning frameworks like LangChain and LlamaIndex. Choosing the right tool for the job. Selecting the appropriate vector database for a project requires evaluating trade-offs across several key dimensions. An interviewee should be prepared to justify their choice based on the specific requirements of a hypothetical scenario. Scale and performance. For initial prototyping or applications with fewer than 10 million vectors, Chroma's simplicity and ease of use are ideal. As scale increases to the tens or hundreds of millions of vectors, managed services like Pinecone or the managed offerings from Weaviate and Qdrant become strong contenders. For extreme billion-vector scale, the robust, self-hosted architecture of Milvus or the proven serverless scaling of Pinecone are the primary options. Operational overhead. The choice often comes down to a build versus buy decision regarding operational management. For teams that want to completely offload infrastructure management and benefit from a serverless model, Pinecone is the leading choice. For those who desire the flexibility of open source but prefer a managed service, Weaviate and Qdrant offer a compelling middle ground. Teams with strong in-house SRE and data engineering capabilities may opt to self-host Milvus or Weaviate to gain maximum control and potentially lower costs at a very large scale. Feature requirements. Specific application needs can also drive the decision. If advanced hybrid search, seamlessly blending keyword and semantic search, is a critical requirement, Weaviate's modular architecture is a distinct advantage. If the application requires tunable consistency levels or support for a wide variety of specialized indexing algorithms beyond HNSW, Milvus offers the most flexibility. The following table provides a concise summary of these comparisons, offering a structured framework for evaluating the leading vector databases. Capability: Pinecone, Weaviate, Milvus, Chroma. Deployment model: fully managed, serverless. Open source and managed open source, with compatible managed options. Open source, embedded or single node. Core architectural philosophy: minimal ops, ease of use. Decoupled storage/compute modularity, flexibility. Hybrid search, massive scale, disaggregation, tunability, developer experience, lightweight, simplicity. Key strengths: effortless, serverless scaling, production-ready reliability, simple API, strong out-of-the-box hybrid search, pluggable modules, proven billion-scale performance, independent scaling of components, extremely easy to start, great for prototyping and local development. Ideal use case: teams of any size wanting a reliable, fully managed service without operational overhead. Production applications requiring flexible, powerful hybrid search capabilities. Large enterprises with massive data sets and dedicated data engineering/ops teams. Developers prototyping LLM apps or building small to medium-scale internal tools. Conclusion: the landscape of data management and artificial intelligence is being reshaped by the symbiotic relationship between vector databases and large language models. This report has detailed the fundamental principles that underpin this new ecosystem, from the mathematical representations of meaning in vector embeddings to the sophisticated algorithms that enable efficient search at scale. Understanding vector databases requires a grasp of the shift from exact match to similarity-based retrieval, a change necessitated by the proliferation of unstructured data. The effectiveness of this retrieval hinges on the quality of context-aware embeddings produced by models like SentenceBERT and the appropriate application of similarity metrics like cosine similarity. To make this technology practical, ANN algorithms such as HNSW and compression techniques like product quantization are employed, creating a system that balances speed, cost, and accuracy. These technologies converge in the Retrieval Augmented Generation (RAG) framework, which grounds LLMs in external, verifiable knowledge. RAG mitigates hallucinations, provides access to current data, and enhances user trust, representing a more modular and scalable architecture for AI. The performance of RAG systems can be further refined through advanced strategies like intelligent document chunking, the use of re-rankers for a second pass of filtering, and sophisticated retrieval patterns like the parent document retriever. Finally, the choice of a specific vector database, be it the serverless simplicity of Pinecone, the modularity of Weaviate, the massive scale of Milvus, or the developer-friendly nature of Chroma, is a critical engineering decision based on trade-offs between scale, operational overhead, and specific feature requirements. A thorough understanding of these concepts, from the foundational theory to the practical application and ecosystem trade-offs, is essential for navigating the technical landscape of modern AI systems.